everyone. So let's get started in Pset 3 solutions. So let's take a look at the first problem. So let's take a peek at the snapshot of 3D particle growth. So red is our average particle size. So if we're looking at our red particle, A is equal to A bar. And we need to indicate with a circle, use a different color, black, a circle which particles will grow, and a check mark on which particles will shrink. So we know that based on we're looking at, again, particle sizes, 3D particle growth. So we know our criteria from our lecture notes, that if A is greater than A bar, then dA dt is greater than 0. If A is less than A bar, then dA dt is less than 0. And if A is equal to A bar, our dA dt is equal to 0. How do we know that? And does that make sense? Remember, we always move from where? From high chemical potential to low chemical potential. And we know that our chemical potential is proportional to our curvature, which is equal to 1 over r, approximately, again, proportional. So again, if I have a very, 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 very large radius, that means I have very, very, very low chemical potential. If I have a small radius, I have high chemical potential. So we are going to move from high chemical potential to low chemical potential. So the big particles are going to grow at the expense of small particles. So the ones that are going to grow are everything greater than this. So this guy's going to grow, 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 and these guys are going to shrink. So the shrinking ones are my check, and that's it. Excellent. Number 1's done. So write out the chemical potential for the purple and yellowish, purple/yellowish orange, so this guy and this guy, and then which will grow, which will shrink. Where will the atoms flow, indicate in the Bell reaction curve in figure 2 by labeling the wells. So we know that in general our chemical potential, mu of a sphere.
The chemical potential of a sphere is the chemical potential of an infinite plate plus or minus 2 gamma surface tension V bar over R. So whether that is positive or negative, or the relative magnitudes for sphere, it's going to depend on, again, the size, the radius of our particle. So we've written out the chemical potential. Good. We know that the chemical potential of my purple is going to be less than the chemical potential of my yellow, orange, whatever you want to call that one. So excellent. Which one will grow? Which one will shrink? So we already kind of discussed that. So we know that this guy is going to grow relative to this little guy right here. How do we know that? Because, again, we had this kind of gradient in chemical potential. We go from low to high. That's where the atom flux will go. So the atoms are going to flow from yellow to here. Again, high chemical potential to low chemical potential. And we can also label that. So where are we going to jump here? So if I'm sitting here, I want to make the short jump. So I'm going to go from yellow to purple. I don't want to go from purple to here. That's a larger energy barrier jump. So, good. This one guy is done. Look at the plot of the log, base 10, not natural, of the average 3D particle radius versus log of time. What is the slope of each curve? Rank which of these curves occurs at the highest temperature. Justify your answer, be specific, relate to relevant equations. What does the y-intercept of the curve signify? So we need to go back and look at, we have an equation, a cubed minus a average a bar not cubed equals, let's kind of go all the way into our, not lecture 4, we need to go all the way into lecture 6. So let's go to lecture 6. I've got a bunch of writing around here. Let's go to our relevant section here. So we want to go to our equation for our, not that one, almost there. We want to look at this equation here. So this is our equation for Oswald ripening. So we have this and we have this. So we know that the average particle size scales as t to the 1/3. So if I take the log, not the log base 10 of this, I know that my slope is going to be, basically my log of a bar, and it'll be, if you take the log of this, the slope will be 1/3 times log base 10 of t. And then if there's some prefactor next to this, let's call this, b, the log, this is just basically going to have the form of this, log a bar plus, or equals, log of b plus 1/3 log of A, or T, excuse me, time. So that's kind of the form. So when you have, let's kind of actually scroll down here. Let's write that a little bit nicer. So if I have an equation that looks like A bar equals basically this slope, let's call this, let's kind of explain this clearly. So I have this slope right here. Let's call all this, stuff B. So if I have an equation A equals B times T to the 1/3, if I take the log base 10, log of A bar equals log of B plus my log of T and then 1/3. So if I'm looking at a plot of this versus this, i.e. this being my x, my slope is going to be 1/3, and my y-intercept is going to be controlled by this right here. So this is a constant, this is a constant, this is a constant, this is a constant. So I'm basically controlled by d over t. And I know that d equals d naught exponential minus qa divided by kt. So I have this Arrhenius relationship. So this 1 over t at high temperatures is going to be dominated by that exponential relationship. So as my y-intercept value, which is controlled by this factor, as my y-intercept goes up, my temperature goes up. This exponential relationship beats out that 1 over t. So going back to our problem here, I know that the slope here, they're all equal, and that should be 1/3. And I know this y-intercept means that temperature is increasing. All right, we've got this one. If I'm nucleating these particles from liquid solution, what free energy term pushes me to nucleate a solid, and which free energy term pushes me to stay a liquid? So we know that we want to, actually let's go into our notes again. So let's look at our kind of free energy equation for nucleation. And let's go to our clean page here. So let's go to our nucleation growth section. So this is our final free energy term for nucleating a particle. This term is negative. So to nucleate a particle, this is driving us forward. What is that? This is the volumetric term. So the binding, essentially, it's the amount of undercooling, et cetera, et cetera, et cetera. Actually, we have this equation right here. So as we get colder and colder and colder, we want to nucleate a particle. We want to kind of create a solid. The thing that pushes us to be a liquid is this surface term. So the surface fights against that because it's costly to create an interface between liquid and solid. Those are bad interactions. So it's only when I have a huge particle, when I have a really, really small particle, I'm creating a lot of interface relative to my volume. So a small particle has really, really, really poor volume to surface area ratio. Here, I've got lots of volume, lots of good solid-solid interactions that will essentially offset these unfavorable liquid-solid interactions. So that's pretty much the answer there. Nice conceptual question. So here we go. My undergraduates actually measure the free energy for nucleation as a function of particle radius, as shown below in Figure 4. On the blue curve, indicate the critical radius and also which will grow and which will shrink. So this is my critical radius occurs when my free energy is, this is going to be my R crit. I know that on this side, I'm going to grow. Why? Because if I move further to the right, my slope is decreasing. So a spontaneous reaction is when delta G, d delta G dr is less than 0. So the change in my free energy decreases. If I go here, if I want to grow, it actually increases. So here on this side, I'm going to shrink. So let's see what the question is asking. So let's go back up. Blue curve indicate the critical radius. What radii will grow and shrink? We got it. And then we explain basically free energy consideration changes. And again, small critical radii is the same idea. Small radii, high surface area, low volume. Large, basically large particle sizes will grow because large volume, small surface area. What is happening with other curves? Explain why these curves are shifting and what can happen. So if we go back to, we have a function, or we actually have an expression for R crit is defined as follows. So let's go into our lecture 6. So our critical radius is defined as follows. This. But we also have to remember that delta GV is a function of essentially undercooling here. So we could plug this back in. So R star is also equal to 2 gamma SL over basically delta HF, delta T, and then Tm on top here. So constant, constant, pretty much a constant. Delta T is our Tm minus T. So the larger that value is, the colder our temperature is. So as we decrease temperature, our critical radii does what? It gets smaller and smaller and smaller because we want to grow more of those, or nucleate more of those particles. Excuse me. I'm going to always say growth and nucleate, but it means we need to nucleate. So if I'm looking at this curve right here, this is saying that my critical radius increased. What does that mean? My delta T decreased. My temperature increased here. What about here? Well, this is heterogeneous nucleation. We're creating less surface area when we're nucleating on here versus in a vacuum for here. So that green one is heterogeneous. If I were to increase basically my undercooling or decrease my temperature, my curve would shift over here. So cool little example. Excellent. Number 6, what is the average particle size of each system? Such that for A, B, and C in figure 5, what systems will particle grow? How will the growing scale in time? What assumptions do we make? So we are looking here at a plot of dA dt versus A. So again, if we go back into our lecture notes, we know that if we find the particle size that grows the fastest, if I take this function this beautiful function here, dA dt, which tells us again that if A is greater than A bar, dA dt is positive, A is less than A bar, dA dt is less than 0, it's greater than 0. If I want to figure out what particle size is growing the fastest, maximum growth rate, I can just take the partial derivative with respect to A, set it equal to 0, and we know that value occurs, once we kind of do all the math, that value where this is maximized is where A is equal to 2A bar. So if I'm looking at this problem here, I can go ahead and find that then this maximum, which is located here, actually here, let's draw a little bit straighter. So this would be my here, here, and let's just say it's right about here. So those would be my A bars. So let's go ahead and pull up Mathematica, or 2A bars, excuse me. So I need to solve. So my A bar is equal to basically, let's call this probably like half dab in the middle. So let's just call it 0.00, let's see how many, 4 O's, 25, and we can divide it by 2, because again, that's 2A bar. B, let's call that, again, BA bar, let's call it 0.00, let's call it like 3, like 2, 3, 4, 3 divided by 2. And then let's do CA bar, A bar equals 0.12345 divided by 2. So if I'm looking, I want to see for what system, let's read the question. For what system will a 45 micrometer particle grow? So let's see, is 45 times 10 to the minus 6, because we know to grow we need our A, this is our A, is A greater than A bar. So that's the condition we need to hit. So is A greater than A bar? So is this greater than AA bar? True? All right. What about for B? BA bar. True. And then what about C? CA bar. Good. That's it. And again, the assumption that we're making is that the growth scaling in time, we say that our average particle size grows as t to the 1/3, and that is due to the fact, again, we're assuming that the growth is dominated by this maximum particle growth rate, A equals 2A bar. This is the particle size that dominates essentially the growth behavior of our system. All right, 6, 7, let's go ahead and look at this. So 7, which curve is homogeneous? Which is heterogeneous? Where is nucleation dominating? Where is growth dominating? Explain how you write the conclusions via the critical amount of undercooling. Which is easier, homogeneous or heterogeneous? So we know that homogeneous is much more difficult than heterogeneous. Why? Because we said that the only thing holding us back is the creation of the surface energy. So it's our surface area term. So that surface area term. So for homogeneous, which is this system, versus hetero, for the same particle size, I'm creating basically double or more surface area than for the heterogeneous. So heterogeneous is easier in the sense that the critical amount of undercooling, i.e. this, which is Tm minus T, I'm going to need less undercooling, right? Because again, we had the competition between volumetric and surface area. And in here, we saw that as temperature decreases, this guy increases dramatically. So as I get colder and colder and colder, I want to kind of create a particle. So I could nucleate and start nucleating a particle at higher temperatures. So if I'm looking here at temperature, I could already start nucleating here, so I know this is hetero. I know this is homogeneous. Based on that, I need less critical amount of undercooling. I need more undercooling, colder temperatures on this side. So if I look at this particular particle, I know that growth is dominating here. Why? Because growth is dominated by diffusion. That is an Arrhenius relationship, minus QA divided by KT. And here, on this side, I know that nucleation is dominating. Why is it dominating? Because, again, my temperature is very, very, very low. And my Arrhenius relationship there is essentially governed by that delta GR equation. So, yeah, that's pretty much it there. And finally, for number 8, I'm producing titanium sheet for aerospace applications. You take microstructure right after rolling and at various times plan to anneal at 800 C. Rank the images in terms of annealing time. Basically, when you place a material in a furnace for a given temperature, how can you determine which grains will grow? How will the grain size scale with time? So here I'm working with grains. So we had a relationship, r bar squared minus r naught squared equals basically something here where we found that there's a relationship again with kind of this exponential minus delta G divided by KT over T. So again, this kind of slope will be dominated by this Arrhenius relationship with temperature. So at high temperatures, this will be positive, and we saw proportional to T. So our average grain size will grow as T to the 1/2 power. So that's for 2D grains. And for 2D grains, we also had our von Neumann principle, which said our n equals 6 rule. So if n is greater than 6, dr bar dt is greater than 0. If n is less than 6, dr bar dt is less than 0. So that's how we can tell on each of these plots how, which grains are going to grow, which grains are going to shrink. That n equals 6 rule. And how can we kind of arrange them in terms of time and temperature? So we're at a fixed temperature. So we're asked, okay, we already answered this. How will it scale with grain growth? How grain size scale with time? Basically r bar to the v1/2. How can you determine which grains grow? Von Neumann principle. And we need to rank them in terms of annealing times. So we're seeing that the grains are kind of growing here. So this I'm going to solve this time 1, time 2, time 3, time 4. So time 4, let me kind of write this a little bit nicer. Time 4 is greater than time 3, is greater than times 2, which is greater than times 1. So we're increasing in time as we go from here, here, and then here. Because if you look at it, our average grain size is growing. That's it. Problem set 3 in the books. Problem set 4, one more to go, and then you're free. All right. Have a great one, and I will see you in lecture. Thanks.